Welcome back. It has been a fascinating journey and I hope you are enjoying the lectures. We have been discussing now more of topics that is related to the research or MSc students and PhD students. So, in this lecture what I am going to discuss is in the previous lecture I discussed aerosol formation, and then we talk about secondary aerosol formation. I gave the examples and then things related to that. In this lecture, because we know that now we have two types of secondary aerosol formation. One is actually secondary organic aerosol formation and the other one is actually secondary inorganic aerosol formation. So, we have seen this evidence that secondary organic and inorganic aerosol formations, they significantly affect the air quality, chemical composition and optical properties. So, the next question, and then there has I also showed in the previous lecture that there have been increasingly very high quality research that has been published in science and nature journals, and which make it more impactful to see why this secondary aerosol and especially secondary organic aerosol formation is very important. Unfortunately, in India we do not have much research on the secondary organic aerosol formation. This probably because it needs lots of intensive field investigations, or you have to go with the kind of modeling studies that are there. So, when you are having modeling studies, this needs lots of computational skills, then some of the times which we do not have. Secondly, the modeling involves lots of intensive chemical processes which often we do not have. I mean, many of us might not be from the chemistry background. So, it becomes very imperative that how you can actually simulate these kind of formations. So, you need to understand the mechanisms, the reaction intermediates that are formed, and then kind of what are the final products and then what is the yield. So, there are so many things that are complicated, but do not worry, I am just going to make things very simple here. I will give just very basic things about this. So, let us start. So, this slides I showed and I explained a kind of fog haze formation over Indo-Gangetic plain, and we found here, I mean I discussed that the chemical analysis or chemical composition was dominated by carbonaceous aerosols. About 60% of that was total carbonaceous aerosols and 20% was about WSIS, water soluble inorganic species. So, this gives a very clear idea that yes, and in the other part we discussed that secondary aerosols are very important. So, TCA includes secondary organic as well as primary organic aerosols and of course, black carbon. So, this means primary emissions are always contributing because they are directly coming into the atmosphere in the particulate form, but secondary aerosol formation becomes very important, and sometimes we have to depend on the proxies to understand this process. So, let us see how we can study this one. One of the way is actually, so the next slide shows that do we have any evidence of secondary organic aerosol formation in the Indo-Gangetic plain. I hope I have shown you these slides earlier as well. So, if you see these ratios somewhere around 0.3, between 0.3 to 0.4, this WSOC to OC ratio, okay, and this ratio is very characteristics of primary emissions. Okay. And I discussed this, that as you move forward to the high Indo-Gangetic away from the Indo-Gangetic plain, the ratio starts increasing, and the WSOC2 ratios at Manora Peak, Mount Abu and National Climate Observatory in Pyramid, the ratio is about somewhere around 0.65 in the National Climate Observatory. You have about 0.6 at Mount Abu and 0.55 at Manora Peak. Now, this kind of and you see the typical primary emissions ratio somewhere around 0.3, 0.4. So lying between 0.3 and 0.4. So how do you know that whether there is secondary formation? So one things that when I was reading the papers, and because we were lacking lots of infrastructures, and through reading some of the papers, it came to my mind that let's do day and night sampling. Okay, so D stands for day and N stands for night. So let's do day and night sampling and see if the WSOC2 ratio is different or same in these aerosols. The idea was very simple, that during the daytime we have more of photochemical oxidation. So the photochemical oxidation driven reactions that will be prevalent, because we have adequate sunlight. We need OH radicals for oxidation, which can be supplied from the kind of water vapor that are there, which can be oxidized in presence of ozone. We will come to that in later slides. So let us see that what the number speaks. So if you see this number, its number is somewhere around 0.5 or 0.45. Just let me see exact number. But before we see what you see, during this period what we found, that the ratio, this WSOC to EC ratios in the daytime and night time. In the daytime the ratio was elevated, it is about 6.7, and in the night time the ratio was 5.6. Now I have told in the just few lectures back that this organic carbon, this includes OC primary plus OC secondary, and this means because day and night time on the same dates, there is not much changes in the emission sources. Almost we can assume that the sources remains the same. So if the sources are remaining the same, then OC to EC ratios will be similar. They are similar, slightly different of course, and here this gives us some sort of hint that probably we have more of secondary organic aerosol formation in the daytime, and because this primary is constant and primary is constant here, on top of this you are having something like secondary organic carbon that is produced during the reactions in the daytime. So in order to further infer this one, I gave the idea of WSOC to OC ratios as an indicator of secondary organic aerosol formation. So we measured and we found that WSOC to ratio is around 0.66 and in the daytime, and if you compare the ratio in the night time, it is only 0.46. So this means there is actually almost like 0.2 unit increase in daytime. Okay. This, when we combine with the OC to EC ratios, gives a very clear idea that yes, we do have secondary organic aerosol formation in the Indo-Gangetic plain, and there is relatively high WSOC to OC ratios during daytime. This suggests enhanced secondary organic aerosol formation during daytime. So this was the paper. This was, of course, this another very important thing is that this we did only 1 week sampling here. I mean we had 1 or 2 weeks, not long term sampling, and when we submitted the papers, we got the reviews, and one of the reviewer was very critical that the data statistically is not very powerful, so you should have more number of data points. But then other reviewers were very positive. They said that this is really a very good idea, and because they just did a kind of simple experiment, but which is directly relevant to the current scenario of secondary organic aerosol formation. After a careful revision, couple of revisions, the paper was accepted in atmospheric environment in 2011. So you can see these papers, and this paper has been actually, it has got a lot of citation, and not only citation. After our paper, there are lots of studies that have been conducted on day and night time. So just to again see whether this kind of things are happening in the atmosphere or not. So yes, we had this evidence, and the way it works actually, if you see here, I have been discussing this one for a long time, and I hope that you have now understood that this kind of primary emissions when you have, so it emits not only volatile organic compounds plus carbonaceous aerosols. It not only emits carbonaceous aerosols, it does emit huge amount of volatile organic compounds, and these volatile organic compounds reacts with this is OH radical, which is actually oxidizing species, and then NOx is also produced. So NOx radical, nitrate radicals can also contribute to this one. They can form some kind of intermediates. We will come to that one. In the gas phase, they will fall secondary organic aerosol in the intermediate phase, and then in the particle phase through the kind of what you call partitioning between gas and particulate phase. There will be a partitioning, and some of the aerosols, secondary organic aerosols, which are actually in the vapor or gaseous form, they will be converted to the secondary organic aerosols through their just kind of deposition on the surface. The limiting factor in the secondary organic aerosols are, if you see here, because this is driven by the sun. So if you don't have sun, you really need sunlight. So sun is very important because of to conduct or to overcome this photochemical oxidation reactions. So we need sunlight, and then you need OH radical. Second limiting species is actually like you have a OH radical here, because those OH radical is the oxidizing species which will react with precursor gases to form secondary organic aerosols. In the daytime, this water vapor and ozone, they will be in the presence of sunlight, they will be actually producing a lot of OH radical. So actually this reaction is limited because of the unavailability of OH radicals in the night time. So in the night time you don't have any sunlight, so this means you will not have any OH radical. So there will no OH radical will be formed, and if there is no OH radical, what will happen? So you will the photochemical reactions, photochemical oxidation reactions that was happening in the daytime will be stopped. So but remember that we do have actually kind of secondary these precursor gases, because there are two things that you need. One is VOC, and then one is actually like oxidizing species. So in the night time we do have adequate amount of VOCs, but they are not getting oxidized because we don't have oxidizing radicals. Although some of the radicals can be actually powered by nitrate radicals in the night time, because in the night time nitrate radicals becomes important, but this is not comparable when you see the secondary organic aerosol formation with the precursor gases and OH radicals. So this becomes very important, and then lots of research have been conducted on. Then we will you can see this one. So this was another paper. You see here, I would like to draw your attention here to this graph. Actually this graph is actually increasing WSOC to OC ratios, and WSOC to OC ratios is plotted on the y-axis right side. So what you see here, as you move from January, February, March, April, May, June, what is there? TCA, if you just calculate total carbonaceous aerosols, which we defined in the previous lectures, TCA as 1.6 into OC plus EC, we take 1.6 as a for urban aerosols. So as you move from winter, so this period is actually like winter, and as you move from winter to summer, what is happening? Total carbonaceous aerosols is decreasing, which should be, because in the summer when you move, your boundary layer gets up, and then not only that boundary layer gets up, you are actually having less biomass burning emissions, because the temperature is already high. So one of the factor that in which the biomass burning is conducted to keep the houses warm and kind of this is actually switched off or it is not there. So, once it is not there, what will happen? The carbonaceous aerosols that is there in the atmosphere, it will be decreasing. And we also did this experiment to see during summer time, and we found during summer time this PM10 was correlating with the calcium, and calcium is actually an indicator of dust aerosol. So, you can see in the summer, spring and summer, spring was just remember that we called spring. There was some very interesting data in this one. We had to define this one, so we just take March as a spring period. And if you see here, that quite good correlation between PM10 and calcium. So, this indicated that the majority of the PM10 is dominated by the dust aerosols. But in the winter time, you see the ratio was OC and potassium. The correlation between OC and potassium becomes very important during winter time and post monsoon. So, this means this ratio is more important, where in the summer season you see the data is clustered here. They do not see any kind of significant correlation. This means this organic carbon that is there is not derived from the biomass burning emissions or there are other sources that are actually influencing the organic carbon concentration in the atmosphere. So, coming back to this, and the increasing WSOC ratio to OC ratios, if you just remember the previous slides, I told that actually sunlight is very important, because it will only it will produce kind of photons which will react with water vapor and ozone. They will dissociate and this will produce OH radical. So, once you have OH radicals, this OH radical will react with the VOCs and this will give rise to the secondary organic aerosol formation. So, during as you move from the winter to summer, there is another very good concept, that in the winter period the sunlight is not that prominent. So, the photochemical activity is slightly slower compared to those in the summer time. So, the HNU or the photochemical activity, this increases during the summer time. This means you have more of SOA formation. This means the WSOC to OC ratios, this will further increase. That is what we see here. And as you move in the more towards post monsoon to winter season, the ratio decreases. You can just use the same analogy, that in the kind of post monsoon, the ratio the activity, photochemical activity is slightly higher or higher compared to those in the winter time. So, you will see decrease in the WSOC to OC ratio. This was another very important finding which indicated, kindly note that before we established these facts, there were very little information on secondary organic aerosol formation in India. Almost there was no information. So, we in fact, I was lucky enough to get into those research at a very right time, because those periods the research on carbonaceous aerosols were actually increasing extensively in India, and I jumped into that one probably in a very good time. So, now then okay. So, now we have kind of fair idea that how the secondary organic aerosols are formed. We understood little bit of the reactions. Now, I am not going to give much more details on that one, but then question remains that how to estimate secondary organic carbon or SOA. Just remember that SOA is actually, if you just multiply by some conversion factors, SOC, you will get SOA. Sorry. So, if we talk about the estimation of SOC, this method is called the EC tracer method. Okay, and then probably why it is called EC tracer method, because here the OC to EC ratios is used. Now, what is there actually? So, in the EC tracer methods, if you just measure OC primary, what will be the OC primary? If you just have known OC to EC ratios, okay, and you just multiply by EC, okay, and here it is important that because we are measuring primary, this should be primary ratio, and as you know, I have been discussing in the previous slides that this primary means there is no secondary organic aerosol formation. So, this in a way you can say that okay, this is actually OC to EC minimum ratio, because this will have no SOA or no significant SOA. So, this is precondition that you assume that secondary organic aerosol formation in the samples which has been taken, okay, for representing this OC to EC minimum ratio or OC to EC primary ratios. They do not have significant secondary organic aerosol, because if they have, then your estimation will be different. So, this is actually OC primary. So, you can just calculate SOC is equals to OC total minus OC primary, and then you can just measure OC total minus, you can just use OC to EC minimum into EC concentration. This is a very simple method. It has been used during the initial days and lots of studies were conducted. So, the precondition that actually are that both OC and EC are derived from the same sources. Contribution of SBOCs are negligible here, and therefore, the secondary and the kind of in the OC to EC minimum ratios, the composition of primary carbonaceous aerosols should be the same to that of the source. So, that the characteristics of primary carbonaceous aerosols does not change during the course of sampling. So, this is very important that these conditions are met, and you can just use this one. And so, this is actually like I talked about the EC tracer method, how to apportion this one. There are actually positive matrix factorization analysis. Again, if you do on the filter analysis, like you have offline methods. So, if you have just filter based data, you can just calculate these data and you can use to calculate the secondary organic aerosol. So, one of the methods I told you actually like EC tracer method, the other method is actually positive matrix factorization. It is kind of more of statistical, where some priori knowledge about the sources and some diagnostic ratios and concentrations are needed. So, you put the data, I am not going to discuss that in the details. And then there are actually now more online measurements like aerosol chemical speciation monitor, ACSM. You have actually online aerosol mass spectrometry. They give actually directly data about SOA, and they not only give, they give further more data that you have oxygenated organic aerosols, you have actually biogenic oxidation aerosol. So, there are lots of other things that you can get from the online measurements which is taking place. In India, we do not have much of the AMS aerosol mass spectrometry. There are a couple actually, one is in IIT Kanpur with Professor S.N. Tripathi. So, he is extensively doing this kind of studies. ACSM is there in probably in physical research laboratory, and then we have one in IITM Pune, and then couple of more institutions. These are very expensive instruments, so they you need to get fund for that, and because of this lack of funding, sometimes it becomes very difficult to do the analysis. But if you just do this one, offline methods, the good advantage of an offline method is that you can also measure a couple of more parameters in that one. So, that's the advantage. The second method is actually like of modeling of SOA. So, the way you do, now I think you have been very much clear about this one, that anthropogenic they emit primary organic aerosol, semi or intermediate volatile organic compounds. You have biogenic VOCs from biogenic sources. Then they undergo oxidation or aging process and give rise to the secondary organic aerosols. This is there, and model. So, so what will happen if you want to model this one? What are the things that are actually here? That oxidation. So, this means oxidation means you need to know our OH nitrate radicals, and then ozone. I mean, these are the 3-4 key oxidizing species that are there. So, you need to know their concentration, as well. So, knowledge of concentration of precursors and oxidizing species that are there actually. So, what are the precursors that are there actually? There are, as I told, that there are more than 100 or more than 100 cells. So many actually VOCs that are there. So, you have to know the knowledge, you have to have knowledge of concentration of precursors, then oxidizing species. You need to know the oxidation rates and their oxidation processes affecting SOA formation, such as volatility, intermediate that are formed, then partitioning between gas to particulate phases. This is actually phase, etc. So, there are many things that are actually needed, and because of this one, this needs a very kind of computive studies. This is again the same schematic is shown here. You need to know OH, these are the oxidizing radicals. When they react with this one, volatile intermediates are formed, then in between you have organic compounds that are formed, semi-volatile organic compounds are formed, and there is a partition between gas to particle phase, and then aerosol particles are produced. So, this is because this needs a kind of intensive data and intensive research on modeling of SOA, and it not only, you need not to be only knowing about the modeling. Generally it happens that if a modeler probably don't know much about the chemistry that is happening, so the research is hampered there, or some of the chemistry persons are there. For example, like us, we know chemistry little bit, but we don't know computation. So, computation is, we are lacking in the computation. So, it becomes very important. Therefore, you need a team which has a knowledge of both actually. So, which can be combined. One of the things that is another coming to primary and secondary organic aerosols. One of the things like how to differentiate these two. I think I have been discussing about OC to EC ratios. I have given so much information about OC to EC ratios. I talked about potassium to OC. Of course, I talked about I talked about now the correlation, but correlation. Okay, so you can just do this correlation studies, and then potassium to EC correlation we talked about. But if you don't have, not only that, the ratios are also very similar. The ratios, specific ratios can be used to infer whether they are actually biomass derived or fossil fuel derived. Then we talked about you can also use significant physical properties like solubility in water, which you can distinguish with the WSOC to OC ratios. If the aerosols are having more of secondary organic aerosols, then WSOC to OC ratios will be high, but in otherwise the WSOC to OC ratios will be lower. Then other methods are like tracer methods, wherein you can use oxidized pHs and you can use selected pHs as well. So, usually in the primary emissions, the oxidizing pHs will not be there, but when you have a kind of secondary organic aerosols, this will have more of oxygenated pHs. So, based on those treated precursors, you can also do some of the studies that also use carbon 14 to distinguish the sources of primary as well as primary carbonaceous aerosols, especially the fossil fuel and biomass burning. So, I think we discussed a lot about the secondary organic aerosols, their formation mechanisms, how to distinguish between the two, what are the methods that we can use to calculate the secondary organic aerosols. I have not given a very elaborate or kind of examples with the examples, but yes, these are very important things that need to be studied, and I think that in the coming futures some of the students from you must be doing kind of a very good research on these secondary organic aerosols. So, I think the secondary organic aerosol research will still be there for another decade or two, because lots of things are still misunderstood or not understood properly. So, with this one, I think I am not going to discuss this, because just to give, because this is actually maybe if you just want to have some idea and just quickly I will browse through. So, you can have carbon 14 carbonaceous aerosols. Carbon 14 is produced by the spallation reactions in the atmosphere, upper atmosphere, and then it gives rise to carbon 14. And as you know that carbon 14 is actually radioisotope, so it decays, and then if you have oxidation, this carbon is oxidized and it will have actually carbon CO2 will be there. And when the plants take these through the absorption, this actually they will take this carbon 14 during this absorption and do the photosynthesis, and when they decompose, this activity, this process will be stopped. So, you have no more addition of carbon 14, but rather you have whatever the plants has accumulated, this carbon 14 will start to decay. So, this will be this sources will have depleted carbon ratios, and this is what is happening if you have kind of we call fossil fuel. So, if you have fossil fuel derived fuels, if you use fossil fuels, they will be carbon 14 depleted. So, you have a kind of carbon rich source, carbon 14 enriched source, and carbon 14 depleted source. So, based on that you can actually calculate that how much actually are there in the atmosphere. So, yeah, this you can differentiate between organic and elemental carbon using these ratios. Not only that, you can distinguish if you just do this calculation on the EC fractions, you will get sources about kind of primary production, like primary carbonaceous aerosols. And if you just do little bit of the on the organic carbon fraction, if you just measure carbon 14, you can get primary and secondary production as well, because this VOCs they will be oxidized, and then during the oxidation process carbon 14 may be actually whatever is accumulated might be released. So, this can be used, and biomass burning and primary combustion, you can just use these things. So, I am not going to discuss these things much details. So, I hope you have understood little bit about the secondary organic aerosols, their formation and how to quantify them. In the coming lecture, we will discuss little bit about the secondary inorganic aerosols, and then we will move forward for the other topics. So, thank you so much for attending the lectures. I hope you are enjoying and doing quite well. Keep reading and studying, and we will meet you in the next lecture. Thank you. Bye bye.